Section 8.5, graphs involving exponential functions. So we've done curve sketching with the usual armory of functions, namely polynomials and rational functions. But you can do curve sketching with any of the functions that we've taught you, logarithmic functions, exponential functions, trig functions. And one of the types of functions which is very important and crops up a lot is exponential functions, so it's important to be able to graph those. So we'll do a whole section on that. And really it's exactly the same as graphing an ordinary function, so I'm not going to spend a lot of time on it. There's a lovely example in the textbook. Right? A lovely example in the textbook of drawing the graph of x squared minus 1 times e to the minus x. And you should really work through that example carefully. I'm going to do a different example, namely sketch the graph of y equals x times e to the minus x squared. Good. So let's begin. We'll use the same process as the textbook uses, A, B, C, D, and working out the domain, the x and y intercepts and so on, all in order. So let's do that. So the first thing we need to do is work out the domain of this function. Now we've got x times an exponential. Inside the exponential is just x squared. There's never any problems here because exponential can accept any number, and so we see the domain is the entire real number line. Okay. Second part of the question is to find the x and y intercepts. So if we find the x-intercept, to find the x-intercept, we must set y equal to 0. When we set y equal to 0, we get x times e to the minus x squared equals 0. Now one thing that's very important to remember is that exponentials can never equal 0, right? E to the power of something can never equal 0. Just remember that, right? If you think of the graph of e to the x, it looks like this, and it never touches the x-axis. So no matter what value of x you sub in, e to the x is never zero. So if I've got something times an exponential equaling 0, the guilty party must be this guy here, x. Cannot be this one. He's innocent. Okay, so if I want to summarize this, so 0, 0 is the x-intercept. One nice thing to do while you're drawing the graph is to draw a sort of dummy graph on the side and work out the dummy graph as you go along. Okay, so here's my little dummy graph that I'll have on the side here. Okay, let me just draw it like this rather. Okay, good. So y equals x e to the minus x squared. I don't know if you can see that there. Let's just move this slightly across. There we go. So what have we just worked out? We've worked out the x-intercept. So every time I've got a point on the graph, I'm going to do it in red. So we've got a single point on the graph. Good. And the y-intercept, we set x equal to 0, and from that we just sub x equal to 0 into the formula of the function. We get y equal to 0. So therefore 0, 0 is the y-intercept. Okay, so that's also the y-intercept. So this the only place in which it touches the x and y axes is at that single point. Okay. What about our asymptotes? What about our asymptotes? So that's question C. We've got vertical and horizontal asymptotes. So as far as vertical asymptotes go, we are the vertical asymptotes. Well, let's remember our formula. Y equals x e to the minus x squared. And there's no vertical asymptotes because this never blows up. Okay, there's no denominator in this formula, so it never blows up. So there's no vertical asymptotes. Horizontal asymptotes. Now we should check what happens as x approaches plus or minus infinity. So as x approaches plus infinity, what happens to the formula for the function? X e to the minus x squared. Well, what happens here? Let's see. This approaches infinity, and this approaches 0 because it's exponentially decaying. Now, to calculate, so this is a tricky limit. I would have to calculate it using L'Hopital. Now, you've done many examples of L'Hopital before, and remember, in the end of the day, once you've done those examples, you realize that exponentials always win. So if there's a battle between an exponential and a polynomial, the exponential will win. The exponential is trying to get to 0, the polynomial is trying to get to infinity. You multiply them together, that's a battle. The exponential is very powerful and it will beat the polynomial. So this tends towards 0. And you can check that if you want using L'Hopital by converting this into a fraction. Anyway, this tends towards 0, but importantly, does it tend towards 0 from above or from below? Well, let's check. This guy is tending towards infinity. This guy is tending towards 0 from above, right? Because exponential is always positive. So we've got a positive number times a positive number. So this thing is positive. So this is approaching 0 from above. Okay. What about as x tends to minus infinity? Okay, now the x is approaching minus infinity. The exponential is approaching 0 from above as before because we've got a square in the exponential. And even if we didn't have a square, we need the square here. Okay, so that means we've got a negative number, a large negative number, times a number that's approaching 0. And this is approaching 0 very fast because it's an exponentially approaching 0. So it beats the approach to infinity here. So it is tending towards 0, which you can check using L'Hopital, but it's approaching 0 from the left because we've got a negative number times a positive number. So this is a negative number. Okay, so therefore y equals 0 is a horizontal asymptote of type. Now I draw my little horizontal line. And as x is approaching plus infinity, the graph is approaching 0 from the right. As x is approaching minus infinity, the graph is approaching 0 from the left. Okay, that's sort of, I like to do it like this so that you can immediately translate that into the graph. Alternatively, you don't have to say whether it's approaching from above or from below. You can just say y equals 0 is a horizontal asymptote, that's fine. But it's not as much information. Doing it my way will allow you now to transfer this information onto your little dummy graph immediately. So over here I just know that x equals 0 is a horizontal asymptote of this type, and over here it's approaching 0 from above. Good. So that actually helped us. We're starting to get the idea of how this graph looks. Okay, the intervals of increase and decrease. And this is the point at which we take the derivative. Okay, so we need to calculate the derivative of the function so we can work out where it's increasing or decreasing. So it's a product. It's x times e to the minus x squared. So it's the first times the derivative of that is the first times the derivative of the second, which is the derivative of e to the minus x squared is e to the minus x squared, times the derivative of the inside, which is minus 2x, plus the second times the derivative of the first. The derivative of x is just 1. Good. Now in all these exponential type problems, it's always going to have that pattern where you'll have, when you do the product rule, you'll have an exponential appearing in the first term and in the second term. So you can take it out as a common factor, and then I've got minus 2x squared plus 1 as my second factor. Right, so therefore we see that the derivative equals 0 precisely when either this is 0 or this is 0. And as I said before, exponentials can never be 0. So he's innocent. This one is guilty. So 1 minus 2x squared is equal to 0, which means that x is equal to plus minus 1 over root 2. Okay, so now we draw our number line. We mark off the points where the derivative is 0. There's one point at minus 1 over root 2, and there's another point at plus 1 over root 2. We then calculate test values inside these intervals. We determine the sign of the derivative at the test value. And we then conclude whether the function is increasing or decreasing. Okay, so in this interval here, I might as well choose a huge negative number, such as minus 1,000, for my test value. When I sub that into the formula for the first derivative, this factor here is going to be a large negative number because it's 1 minus a large number. Because minus 1,000 squared is plus 1,000, so this is 1 minus 2 million. So it's a large negative number, so the sign of the derivative is negative, and so the function is decreasing, which we can draw like that. In this interval here, I can choose my test value to be 0. When I sub that into the formula for the function, this factor here is just 1. This factor here is just 1. So I get a positive number, and so the function is increasing. And here I can choose a large positive number as my test value. The sign of the derivative will be negative as before. This will be a negative number. This is always a positive number. Exponentials are always positive. And so I have a decreasing function over there. So we conclude that f is increasing on, I hope you can see this, minus 1 over root 2, comma 1 over root 2, and it's decreasing on these two intervals here. So minus infinity up to minus 1 over root 2, and this interval here, which is 1 over root 2 up to infinity. You must write out, you can't just draw the table, you must write out. Okay, so I just want to also say that now that we've worked out the intervals of increase and decrease, we should mark that off on our little graph that we're drawing on the side as we go along. So we've just worked out that the function's increasing in this middle interval and then decreasing these outer intervals. So one way that you can mark that off on the graph is by drawing a little dotted line here, and then marking off the same number line as before. So this is minus 1 over root 2, and this is plus 1 over root 2. This number line now lines up with the x-axis in your graph, and you can just say that f is decreasing over here, increasing over here, and decreasing over here. Okay, and you just have a look at your graph and you just see whether that makes sense. So over here it's decreasing, and then up until this point here, and then it's going to start increasing again up until this point, up until some point over here, and then it's going to start decreasing again. Okay, so it's going to go increase, and then from this point here it's going to be increasing, and then it's going to get to some maximum, and then it's going to start decreasing again. Okay, so we're starting to get a shape of a graph here. We can already draw it. It's going to look like this. Okay, but I'm not going to jump the gun. But we can already see that's roughly how the graph is going to look like. In fact, let me do that. Let me jump the gun. So remember, this is a side graph, so we can update it as we go along. So if we discover some data later on that contradicts what we've drawn, then we know we've made a mistake somewhere, and we can go and correct for that. So right now we can see that the only thing that's consistent with the data that we've calculated so far is if the graph looks like this. Okay, this graph is decreasing up to this point, increasing on this interval, and then decreasing again. It goes through the y-axis and the x-axis at 0, 0, and it has the correct asymptotic behavior as x approaches plus minus infinity. Good. So let's carry on. Then you should do the relative min or max. And we drew that table of increasing, where the function is increasing and decreasing. So from that table, we can conclude that this point here is a relative minimum. So that's the point x equals minus 1 over root 2. And y is equal to, well, we sub it into the formula for the function. So minus 1 over root 2 e to the minus 1 over root 2 squared, which is minus a half, is a relative minimum. Because from the table, f was decreasing before that point and increasing after that point. So we're talking about this point here, which is a relative minimum. And similarly, this point here, which is where x equals plus a half, or 1 over root 2, sorry, and the corresponding y value is 1 over root 2 e to the minus a half. I just sub it into the formula for the function. Is going to be a relative maximum, because before that point the function was increasing, and after that point the function was decreasing. We're talking about this point here. Okay. What about concavity? Okay, now for concavity. For concavity, we must calculate the second derivative. So that's the derivative of the first derivative. And the first derivative was e to the minus x squared times 1 minus 2x squared. Okay, so I can calculate. It's again a product rule, so it's the first times the derivative of the second plus the second times the derivative of the first. I group everything together, so I've got an e to the minus x squared. I've got a minus 2x, which I can take out as a common factor. And then what do I have left? I've got a plus 2 from this term. And from this term, I've got a plus 1 minus 2x squared. So in total, I've got minus 2x e to the minus x squared times 3 minus 2x squared. Okay, when will the second derivative equal 0? One of these factors has to equal 0. Exponentials can never equal 0, so it's either x is equal to 0 or this term equals 0. For this term to be 0, we need 2x squared equals 3. In other words, x equals plus minus square root of 3 over 2. Right, so now we can draw our number line. We mark off the points where the second derivative is 0, namely at 0, at minus root 3 over 2, and at plus root 3 over 2. we choose test values in each of these intervals. We've now created 4 intervals. We determine the sign of the second derivative, and we add those test values, and then from that we can determine whether the function is concave up or concave down on those intervals. Okay. So in this interval here, I can choose a test value of -1000, sub that -1000 into the formula for the second derivative. I'm going to get out a negative number times a negative number, because x equals -1000, times a positive number. Exponentials are always positive. So let me just do this again. This is a negative times a negative times a positive. And then I sub in -1000 in here. I get 3 minus 2 million, because -1000 squared is 1,000,000. So that is a negative number. So this is negative. So minus times a minus times a plus times a minus is a negative. So this is sign is negative, so the concave down over here. In this interval here, I can choose -1, because that lies between -√3/2 and 0. And if you work this out again, so I sub in -1 in here, what happens? I get out a minus here, because that minus. I've got out a minus here, because x is equal to -1. Exponentials always are positive. I sub in x equal to -1 here, I get 3 minus 2, which is positive. So I get a minus times a minus, so I get a plus. So it's concave up here. And similarly, if you carry on working out over here, it's going to be, I can use +1 as my test value, I sub +1 in, and I'll get out a negative number, so it's going to be concave down. And then I can use +1000 as my test value, sub +1000 in, and I'll get out a positive number, so the graph is concave up. Okay, so I must not forget to write out my conclusion. So the conclusion is that the graph is concave up on this interval and this interval, so -√3/2, 0, and on this interval here, which is √3/2, infinity, and it's concave down on these 2 intervals here. So that's -infinity up to -√3/2, and 0 up to √3/2. Good. What we should still do is now incorporate this information into our little dummy graph that we're drawing. So we've just determined where the graph is concave up or down. So we look at our graph. Is this information consistent with what we've drawn so far? It's concave. It starts off by being concave down, and then at some point around about here, it changes to concave up. Then at some point it changes to concave down, and then at some point it changes to concave up again. That's consistent with the graph. So we can actually mark off these points on the graph. This would be this point here, right? This is -√3/2, and this point here would be over here at √3/2. These are now inflection points, which we'll do in our next question. And then 0 is marked off over here. See, it's concave up and then concave down. So the great news is that this didn't give us any extra information really. We were already able to draw the graph, but now it's amounted to a check on the sketch that we'd already drawn, and we passed the test. Our graph is consistent with this information. Okay, what about the inflection points? So from the table of concavity that we just drew up, from the table, we found that, remember the table said that it was concave down up to a certain point, then concave up. So therefore the concavity changed at this point here. And so that's a point of inflection. And then the concavity changed again at this point here, from concave up to concave down. And then over here again it changed from concave down to concave up. So there's 3 points of inflection, which I've drawn as big red circles. These other circles are the relative minimum and maximum, which have nothing to do with points of inflection. So the inflection points are at minus root 3 over 2. And I sub in minus root 3 over 2 into the formula for the function. I get minus root 3 over 2 times e to the power of minus 3 over 2. I can also have inflection point at 0. So I sub in 0 into the formula for the function, and I get 0. And then I get an inflection point over here as well, which is plus root 3 over 2, comma root 3 over 2 times e to the minus 3 over 2. I sub that into the formula for the function. Good, and now we simply have to draw the graph. We've calculated everything we need to calculate, and here it is. There's no need for me to draw it out bigger. Our original sketch was correct. The only thing that I should do is I should label very clearly all these points. So what I'm going to do is I'm going to label this point as an inflection point, and then I give its coordinates. So the coordinates are minus root 3 over 2, comma, minus root 3 over 2 e to the minus 3 over 2. This is also an inflection point, so I'll mark that off. Its coordinates are plus root 3 over 2, comma, root 3 over 2 e to the minus 3 over 2. This is also an inflection point. Its coordinates are 0, 0. This is a relative minimum, and its coordinates are minus 1 over root 2, comma, minus 1 over root 2 e to the minus a half. And this is a relative maximum, and its coordinates are plus 1 over root 2, plus 1 over root 2 e to the minus a half. Good.